In this video, we're going to take a look at algebraic proof. Now, algebraic proof can be a really tricky topic. There's definitely some tricky questions that can pop up for this as a topic. Now, before we take a look at these questions here, there's two important things to mention. The first one's about the language that's used in these questions. So there's two examples here. The first one being when we mention the word here, product, and the second one being when we mention the word sum here. Now, if you don't understand what either of these terms means, then you're going to really struggle to actually prove what we want to show here, okay? So when we talk about the product, so when we say the product here of two consecutive numbers, we're looking at the multiplication of those two consecutive numbers. Okay, so product is just another way of saying times or multiplication. And when you see the word sum here, so the sum of two consecutive integers, then this just means that we are adding them together, okay? Another one that might crop up, it's not on this page, but it does come up quite often, is the difference. So when we say the difference, we're just looking at subtraction, okay? So do make sure that you're familiar with those kind of terms. If you don't know what they mean, you're going to really struggle with these type of questions. Now, the other thing we need to understand is how we represent an even number and an odd number algebraically. So for an even number, the way we do this, so for an even number, then we use something of the form, say, 2n, okay? Doesn't matter what we pick for n here, because we're timesing it by 2, it will always be in the 2 times table. Sounds very basic, but it will always be in the 2 times table, and as a result, it will always be even. So that's how we represent an even number, and in that case, if we start with 2n as our first even number, then any odd number will be something of this form. So for an odd number here, if we just show this, then an odd number will be something, say, 2n plus 1. So it'll be the even part plus an odd number. Okay, so the next consecutive odd number here would be 2n plus 3. After that, we'd have 2n plus 5, and so on. Okay, in this case, my next consecutive even number would be 2n plus 2, 2n plus 4, and so on. Okay, so if we were representing these numbers here in order, it would be 2n, 2n plus 1, 2n plus 2, 2n plus 3, and so on. Okay, so you can kind of see the pattern that's being formed here. So let's take a look at this first question here. So I want to prove algebraically that the product of two consecutive numbers is always an even number. So if we just think about this as an actual example here, if I just pick two consecutive numbers, let's just say I pick 5 and 6. Well, the product here just means times these two numbers together. Well, in that case, if I do 5 times 6, we get 30, and clearly 30 is an even number. Let's pick two other numbers. Let's say, I don't know, 10 and 11. So 10 and 11 here. Well, if I times those together, 10 times 11, we get 110, and again, 110 is even. But this doesn't actually prove this. We're just showing a couple of examples here. How do I know that, for example, this works with, say, 105 and 106, 1000 and 1001? We don't necessarily know that it does work. But if we can prove it algebraically, then we know that it will work. So to prove it algebraically, we use these general terms here for our even numbers and our odd numbers. So if I pick an even number just to start with here, so if I do the proof over here now, so for the proof, if I pick 2n as my first number, so 2n is my first number here, then my next consecutive number must be 2n plus 1. We're picking 2n and 2n plus 1 there. So if I find the product of these two consecutive numbers here, that's going to be 2n times 2n plus 1. We're just expanding this bracket here. 2n times 2n would give me 4n squared. 2n times 1 would give me plus 2n. Okay. Now, what we've got here is just this quadratic. But how does this actually show that it's an even number? Well, like we just said here, even numbers, we can essentially always factor out this 2 here. Okay, like you can see here, I can factor the 2 out. That's 2 lots of n plus 1. Same again here, 2 lots of n plus 2, and so on. Okay, so if we can show that here, basically we can factor a 2 out, then we're showing that's an even number. So factor a 2 out here, which we can do. I get 2 lots of 2n squared plus n there. Okay, obviously you can double check that if you expand this back out, you'll get 4n squared plus 2n there. Okay, so because this is of the form 2 lots of something, in that case it must definitely be an even number. So therefore product of two consecutive even numbers, or two consecutive even numbers. Sorry, two consecutive numbers, not even numbers necessarily, is always an even number. Okay, and there we go. So that's all we need to show that. We just need to show that we can factorize it like this. So we can bring out that 2. And there we go. So that's our solution to the first one. Now, just a quick point here. It doesn't matter if you start with, say, 2n plus 3 and then 2n plus 4. If you start with 2n plus 1, 2n plus 2, or if you start with 2n plus 4 and 2n plus 5. I mean, what I would say is just try it. Do pick 2 different examples here, multiply them together, and see if you can factor out that 2. Okay. If I just quickly show just another example here, what I'm going to do is I'm just going to do it in a different pen color just to actually highlight this. So if I pick, say, 2n plus 3 and 2n plus 4, let's just do that. So 2n plus 3 and 2n plus 4. If I multiply these together now, if I find the product, so this is going to be expanding using file, so we get 2n plus 3, 2n plus 4. Expand these out here, I get 4n squared. We get an, so 2n times 4 gives me an. 3 times 2n gives me 6n. And then 3 times 4 gives me 12. Simplify this here, we get 4n squared. 8n plus 6n is 14n. So plus 14n plus the 12. And what you'll notice here is I can factor out a 2. So we get 2 lots of 2n squared plus 7n plus 6 there. Okay, and again, notice we factored the 2 out. So in that case, we've shown that the product of 2 consecutive numbers is always even. So like I said, I just tried a few different examples, make sure that you can actually show that. Okay. But like I said, this one's just an extra solution here. You don't have to do it twice, but just so you've seen that. Okay, so let's move on to the next one here. So if we go back to our original pen color, so we want to prove using algebra that the sum of 2 consecutive integers is always odd. Don't worry about the difference in the wording here where it says integers rather than numbers. Again, we're just using this fact so that an even number we can represent like this, and an odd number we can represent like this. So the sum here, that means we're going to add them together. Again, I'm just going to start with 2n and then 2n plus 1. So that will give me 2 consecutive integers. So 2n and 2n plus 1. So if I add these together now, the sum, we get 2n plus 2n plus 1. In that case, if we simplify here, collect like terms, we get 4n plus 1. Now, what you've got to do here is just think about how this actually shows that we've got an odd number. Well, the 4n here, we can represent that as 2 lots of 2n. So that will definitely be even. And then we've got this plus 1 here. Now, if this part here is even, so this is even, and we add an odd number, so we add an odd number here, then in that case, what we get is an odd number. Okay, so therefore, even plus odd will give us an odd number. Okay. And that's all we need to show there. The main fact that, the main point that we're showing here is that we get 4n plus 1. The 4n here is even, and then that we add an odd number to it means our result here will be odd. Okay. And there we go. So that's our solution to the second example. Moving on to a couple more examples here. Again, I just want to prove algebraically that the sum of 3 consecutive integers is always a multiple of 3. So 3 consecutive integers here, if I just start with 2n as my first integer, I've got 2n, my next one must be 2n plus 1, and after that we're going to get 2n plus 2. Okay. From here now, we're looking at the sum, so that means we need to add all these together. So 2n plus 2n plus 1 plus 2n plus 2. Well, adding all these together here, I'm going to get 6n. So 2n plus 2n plus 2n gives me 6n. And then 1 plus 2 gives me 3. Now, if we want to show that this is a multiple of 3, just like we were doing with the previous examples where we showed that it was an even number and we factored the 2 out, what I want to do here now is factor a 3 out. So what we did here for these, or for this example here, is we factored a 2 out and we showed it was a multiple of 2. So in that case, if I want to show it's a multiple of 3, we factor a 3 out, which in this case we clearly can do because we get 3 lots of 2n plus 1 there. Okay, if you expand that, you get 6n plus 3. So therefore, this is a multiple of 3. Okay, and there we have it. So that's our solution to that example. If we take a look at this one here now, I want to prove that 2n plus 4 squared minus n plus 2 squared is a multiple of 3 for all values of n. Again, same idea here. If we want to show that it's a multiple of 3, we need to be able to factor a 3 out at the very end. So what I'm going to do here is take this expression and just simplify it, because what I'd expect is once we simplify all this, we're going to get something that we can factor a 3 out from. So 2n plus 4 all squared, well, that's the same as 2n plus 4 times 2n plus 4. So I expand this out now using FOIL or any method that you're familiar with. I'm going to get 4n squared. So we get 4n squared there. I get an plus another an, so that's 16n. And then 4 times 4 gives me 16. So that part gives me 4n squared plus 16n plus 16. Now this n plus 2 squared, so n plus 2 all squared. Again, this is just double brackets, so it's n plus 2 times n plus 2 there. And again, just expanding this using FOIL or any method that you're familiar with, we're going to get n squared. I get then n times 2, so that's 2n, and again, 2 times n, that will give me 4n in total, once we collect those together, and then 2 times 2 gives me 4. So here now, what I'm doing is I'm doing this part here, and then subtracting this part off. So what I've got then is 4n squared plus 16n plus 16 minus n squared minus 4n minus 4 there. Okay, remember we're subtracting this off, so everything will become a negative. 4n squared minus n squared, that'll give me 3n squared. 16n minus 4n, that'll give me plus 12n. So positive 12n, and 16 minus 4, that'll give me positive 12. Now, like we did with the previous one, if we want to show that it's a multiple of 3, we want to be able to factor a 3 out from our expression. And in this case, we clearly can. Everything's divisible by 3. So we get 3 lots of n squared plus 4n plus 4 there. Okay. And again, therefore, this shows that we have a multiple of 3. Okay. And there we have it. So that's our solution to that example. Now let's take a look at one more here just to finish with. Again, pretty similar to the last one we've just done, where we showed it were a multiple of 3. This time we just want to show that it's always a multiple of 8 for all positive values of n. Again, just expand these brackets separately. So I've got 3n plus 1. We square all of this. So again, this is just double brackets. You don't have to write the double brackets out like I'm doing here, but I would recommend it if you're prone to making those mistakes. So 3n times 3n, that gives me 9n squared. 3n times 1, that would give me 3n. And again, 1 times 3n would give me another 3n. So in total, we've got 6n. And then 1 times 1 gives me 1. Then we do minus here. So if I just expand this separately here, so n minus 1 all squared. In that case, we're going to get n minus 1 times n minus 1. So that's going to give me n squared. Minus n and then minus another n, so that's minus 2n. And then minus 1 times minus 1 will give me plus 1. Okay, so we get plus 1 there. So again, just take care with the signs as well. Very easy to make a mistake here. So what I'm doing now is I'm taking this quadratic here and subtracting this quadratic. We've got 9n squared plus 6n plus 1 minus all of this here. So everything, well, careful here. So we get minus n squared. This minus 2n now, so we're minusing this negative number here, so that will become positive. So that's plus 2n, and then we minus 1 here. Okay. 9n squared minus n squared, that would give me 8n squared. 6n plus 2n, so that would give me an. And then 1 minus 1, so that would just give me 0. That will just cancel. Okay. Now, because we want to show that this is a multiple of 8 for all positive values of n, we should be able to factor an 8 out. And clearly we can if we look at this expression here. We can factor an 8 out. We get 8 lots of n squared plus n there. Okay. So therefore, this is a multiple of 8. Now clearly as you're working through these, alarm bells should be ringing if you get an expression that can't be factorized or you can't factor an 8 out. Okay, if I couldn't factor an 8 out here and we got to this part, then I know I'd probably done something wrong. So if you get something like that, just go back, double check your working. More than likely you've just made a tiny little mistake. Okay, but there we go. So that gives us our solution and shows that that's always a multiple of 8 for all positive values of n. And that actually brings us to the end of this video on algebraic proof. In the next video, we're going to take a look at geometric proof.